In the last video, we developed Pascal's law, and now I'd like to extend that to start developing ideas on buoyancy and Archimedes Principle. So as a working example here, I'm imagining an ice cube that's just floating in a glass of water. Now we know that there will be lateral forces acting on the ice cube due to the pressure of the water on each side, and that those will cancel. Now, vertically, we have the force of gravity acting down on my ice cube, and we have a force due to pressure from the air on top here. We'll call that F1 for the moment, pushing down on it. And also a force due to the pressure of the water underneath, which we'll call F2 at the moment, pushing up on it. Now, since this kind of pair happens so often, usually this will get rewritten as a shorthand. We define the buoyant force to, as a scalar, to be F2 minus F1. After all, F2 pushes up, F1 pushes down. So the buoyant force will always point up, and it'll be equal to the difference of these forces. So either you can draw this Freebody diagram, or you can draw this Freebody diagram, which is hopefully a little more conceptually straightforward, where again we still have the lateral forces that cancel, but now we just draw gravity down and the buoyant force up. And that's it. So either you draw in the F2 and the F1, or you just draw FB, which bakes the F2 and the F1 into the cake. Now let's try to figure out how big this buoyant force is. So we can start by observing that the depth of the ice cube below the water line, we'll call that H. And the pressure at this location here and this location here are both going to be basically the same. They're going to be atmospheric pressure. Very technically, the air pressure at the top of the ice cube is microscopically lower than the bottom, than at the water line. But really, in practice, this is negligible compared to what's going to be happening in the fluid. Because water has a density of 1,000 kilograms per cubic meter. So we saw that in fresh water, that means every 10.8 meters you go down, the absolute pressure increases by 1 atmosphere. On the other hand, at sea level, the density of air is only a little over 1 kilogram per cubic meter. So basically the variation of pressure with depth is much, much less, and so we can get away with saying that these two pressures here are the same. But definitely the pressure, and then we'll say this is our P1. Definitely down here though, this pressure P2 is definitely greater than P1. No two ways about that. Okay, so let's start to figure out what our buoyant force is equal to. So it would be equal to our F2 minus our F1. And so this will be P2A, where A is the cross-sectional area of the cube, be equal to P2A minus P1A. But now we can, since we're saying that P1, which is technically at this height here, and the pressure here are the same, they're both atmospheric, we can write that P2 by Pascal's law is equal to P1 plus rho g h. And I want to be very, very careful here. And I'm going to write rho sub f, just so we're clear that we're talking about the density of the fluid and not of the ice cube. This will be times A minus P1A. So we can cancel those terms. Okay. Now, if we take this a little further, we get that the buoyant force is going to be density of the fluid times G times AH. Well, this area times this height is a volume. And it is the volume of this region here. Which we'll call V sub D. So this corresponds to the volume under the water line. And if I were in charge of all physics forever and ever, I would just call this the volume under the water line. Unfortunately, I don't have those powers. So the very unfortunate name for V sub D here gets called the displaced volume. Now, other than it is a volume, so at least that part is correct. But the thought of calling it displaced volume is not correct. This fluid that was, the fluid that you would have here need never have existed. It is just simply the volume under the water line. To show an extreme example of this, just to ask yourself, how much water, assuming you had an adequately sized enormous bathtub so that you could float a battleship, how much water would you need in the bathtub? Assume whatever shaped bathtub you need. How much water would you need? Okay, so whatever you thought, it's almost certainly a lot less than you thought. Really, you just need enough to wet the surface of the battleship, and that's about it. To kind of make the point here, let's imagine that we have a battleship that is sitting in some harbor. Let's say it's the SS Physics. And then some supervillain type uses some freeze ray and completely freezes the harbor, freezes the ship in place. So the ship was floating before, and once the ship's been frozen into place, it's still going to be at that exact same depth. Now let's say the captain of the SS Physics orders all hands to grab anything that even remotely resembles a blowtorch and start heating the hull of the SS Physics to start melting the ice in a desperate attempt to break free. So what would happen is you would start to create a layer of melted ice right there. And all the pressures would be exactly the same, because all that matters for pressure is the density of the fluid and the depth. Once we've got the fluid, the depths are all the same. all of the pressures that the battleship will ever see are the same as before the supervillain froze the harbor. So the battleship will float, and it'll float in maybe a liter of water, something like that. You need just enough to barely wet the surface. So, going back to that, so it's a horrendous name, which is why I'm not even writing the horrendous name down. Like I say, I would prefer that you think of this crosshatched region as just the volume under the water line. So the density, so the buoyant force is equal to the density of the fluid times the volume under the water line times G. Now, the buoyant force works regardless of whether the object is a floater or a sinker. If an object is if you have a completely submerged object and it's a sinker, that just means the force of gravity is going to be bigger than the buoyant force, and the net force will be down. On the other hand, if it's a floater, if the object were temporarily submerged, the buoyant force would be greater than gravity, and the net force would be up. It's also possible a neutral buoyancy where they're equal. This is the normal state of affairs for a submarine. They're usually trimmed out to have neutral buoyancy, and then oh, sorry, I misspelled buoyant there. Thought that was looking funny. Normally you'll have normally they're trimmed out to have neutral buoyancy. Much better. And they use the dive planes to basically fly the submarine up and down as they change depths. If they are desperate to get to the surface in a hurry, they will use compressed air to blow the ballast out of their ballast tanks, which will then reduce the force of gravity on the ship because it got rid of a bunch of mass. And so then the buoyant force will be substantially greater than gravity, and they can get up to the surface in a hurry if they need to. But even if an object is just sitting at the bottom of the ocean, there's still a buoyant force on it. So to illustrate that, let's just imagine that I have submerged in an aquarium a scale. And let's just say the scale will read in newtons. And I go stick a cube of iron on the scale. Let's say it's 10 centimeters on a side. We'd like to know what value would the scale read. Well, let's start by drawing a Freebody diagram for the iron cube. So we will have one force acting down on the iron cube. That will be gravity. We will, because we're submerged in water, also have a buoyant force up on the iron cube. And then finally, we will have a normal force acting on the cube as well. So because the cube isn't accelerating, the forces have to balance. So we can say that normal force plus buoyant force minus gravity has to equal MAY, which is 0 because it's not accelerating. So we get the normal force, which is what the scale is going to read, will equal the force of gravity on the cube minus the buoyant force on the cube. Okay. So this will be equal to mg, and this will be, oops, sorry about that, and this will be equal to the density of the fluid times v VD times G. Now in this case here, the cube is completely underwater. So the volume under the water line is just plain the volume of the thing. Similarly here, the density, the mass of the object is going to be the density of iron times that same volume times G. So we can group this out. Density of iron minus density of the fluid, which in this case is water, Vg. All right. So this is the density of iron, roughly, sorry, steel I should say, that's the number I looked up, is 7,900 kilograms per cubic meter. Density of water is 1,000 kilograms per cubic meter. And the block is 10 centimeters on the side. Now we got to work in cubic meters, so this is going to be 0.1 meters cubed, that's the volume, times 9.8 newtons per kilogram. All right, so that will cancel all those cubic meters. This will cancel those kilograms. We're left with newtons. That's good. And we will get 67.6 newtons. And if we didn't have that, it would be almost 10 newtons higher. Okay, in the next video, we will start thinking about what happens if fluids are moving.